yours.
Thank you very much, Hans. Thank you and welcome everyone. I'm actually very pleased that Leonardo Energy and Energy Evaluation gave me the opportunity to present today at this 20th webinar of the Energy Evaluation Academy. So thank you for that. In the following 15-20 minutes, I will present the work I have conducted together with colleagues from the European Environment Agency and with colleagues from the European Topic Center on Climate Change Mitigation on interactions as we follow the path towards more renewable energy in general, and in particular to renewable electricity, the transition to renewable energy and renewable electricity, and the types of co-benefits and trade-offs that sometimes can occur and how these can inform better policymakers. So part of policy evaluation. But first, my name is Mihai Tomescu. As Hans introduced me, I work for the European Environment Agency in the program on climate mitigation, energy and transport. And just to say a few words about the house, about the European Environment Agency, we are one of the first, oldest agencies actually in the European Union. We are located in the lovely city of Copenhagen, which is the capital of Denmark. And our main aim and goal is to deliver timely, relevant data and information to European and national policymakers and to support their policy processes in this sense. And to that end, we work actually with a network, with a very broad network of authorities and competent institutions and authorities across European countries, broader than the European Union. We are encompassing 33 European countries, and we are working very closely together with topic centers. And in the presentation after me, you will hear from Evert, who will be presenting on behalf of the European Topic Center on Climate Change Mitigation. But what do we do on climate and energy, and how did we start this exercise? I think it is relevant to say a few words. The agency is assisting the European Commission and the member states, but as regards the European Commission, we are clearly mentioned under some pieces of legislation, such as the older monitoring mechanism regulation. More recently, it is the European climate law, the European Green Deal. We have a role under the regulation of on the governance of the Energy Union and climate action. And what we do under these pieces of legislation is to support with data, which is being reported in many cases directly by the countries towards the agency through our infrastructure, to quality assure the data, quality check the data, and provide data indicators, assessments, and knowledge back to the policymakers. And on the right side, you will see two illustrations from recent assessments on the progress towards 2020 targets from last year. We're already preparing this year's assessments. To go a little bit further, I think this is the core, and it is rather complex, but what we asked ourselves when we started several years ago to look at these interactions was how we can maximize co-benefits of the energy system transition, and how we can provide this information in a way that is making it more digestible for the member states and may allow them to design their energy mixes and their transition in a way that maximizes at the national level the interactions, the beneficial interactions. And what we know, for example, from this diagram is that on renewable energy, we have a target, we track the progress towards the target, but the target is a share, which means that the less energy we consume, so the more ambitious you go on your energy efficiency target, the easier it is to meet your renewable energy targets. The easier you meet your renewable energy target, the more efficient you are in substituting non-renewable energy sources, which are mainly fossil fuels. So there is a very strong and direct interaction between these three dimensions, which is also why we analyze them usually together. But it is not really stopping here. It also depends a little bit on which renewable energy technologies we consume or we use to generate electricity, if we look at electricity. because depending on the on the energy source, there might be interactions with the carbon stocks and with land use change, and forestry. And there may also be interactions with air pollutant emissions. So we know that renewables are very good for sectoral substitution of fossil fuels. We started with this part on sectoral substitution. We know that they're very important for climate mitigation. They can improve health and they can reduce air pollutant emissions, but this is something that needs to be looked at specifically in interaction at the national level. They usually improve energy efficiency. They have other multiple benefits that are, of course, very important, such as job creation and support as well energy independence. And again, going a little bit backwards, we start by looking at the trends. We get informed about, in this particular case, the evolution of renewable electricity technologies and how this compares with the initial trajectories that member states had set for these technologies in their national renewable energy action plans. It is quite interesting, for example, to see that solar photovoltaics has risen much faster in this illustration than the sum of the expectations of all the countries for 2020, which is actually standing proof for the cost reductions and for the technological learning, rapid technological learning of this technology. There are other technologies that have grown a little bit less fast compared to the predictions, but I'm not going to go here into the details. In terms of the method and our approach to look at these interactions, very simple. What we do is to determine the amount of renewable energy consumed in any country and in every given year, and in each particular sector: electricity generation, in heating and cooling, and in transport. And for that, we rely on data that the countries report themselves to Eurostat, either as part of the energy balances and or as part of the renewable energy shares questionnaires. We then determine reference emission factors for initial energy carriers, which are expressed in primary energy. And we also express the renewable energy sources in primary energy. And what we do is to make a substitution where we use a counterfactual scenario, and we're asking ourselves, what would we have consumed today had renewable energy sources not increased any further since 2005? And we look at how much renewables have increased since 2005, and then we say, well, they have substituted in this proportional or in this equivalent amount these and these primary energy carriers. And for each of the primary energy carriers, we attach greenhouse gas emission intensities, so we can calculate estimates for gross avoided emissions. And in a fairly similar way, albeit a little bit more complex, we do the exercise for air pollutant emissions for nitrogen oxides, sulfur dioxide, particulate matter, volatile organic compounds, and then we see what interactions result. And then in a final step, we try to attribute these observations or these estimates between the emission trading scheme and the sectors not participating under the ETS. And here I'm going to show a little bit about the results. Here are the estimated effects of all renewable energy consumed on greenhouse gas emissions. On the lower side, on the lower line, continuous line, is showing the actual emissions with the European Environment Agency's estimate last year for 2020. The higher line is actually showing how much the greenhouse gas emissions would have been in accordance with the calculation that and the method that I indicated before, had renewables not increased anymore since 2005, our counterfactual. And what we can see is that the greenhouse gas emissions would have been an estimated 12% higher by 2020. This is an estimate. I think it is a good indication. It is not really an absolute number. And the same can be said about the other estimates. Now, going a little bit more detailed into electricity, because it is the main theme of this webinar. The first is actually to say that if you would like to have an interactive version of this data viewer, I will place a link in the chat, and you can go and see on our website this dashboard where you can select on your own both countries and dimensions and impacts. But what I'm going to show here is how the estimation looks in terms of avoided fossil fuel consumptions. The most important thing is that if you consider all renewable energy growth, so not only electricity, the substitution as calculated with this method is of 19% of all primary energy coming from fossil fuels at the European level. So we would have had a 19% higher, so almost 20% higher consumption of fossil fuels without the increase in renewable energy sources. When we look at electricity in particular, we see that the highest substitution is appearing in the countries where basically renewable electricity increased most. And the first graph, the upper graph, is showing the avoided fossil fuels per capita. The lower graph is showing, but it is too small, I can realize that for you to see, it is showing it by country. More interesting, the third graph here is showing what is being assumed to be substituted. And what we see here is that coal is the fuel most displaced in the electricity sector, but also natural gas. The blue bars represent quite a large amount in the substitution effect in the electricity sector. Now, moving over with these interactions, we're looking at sulfur, so the increase or decrease, the impact interactions with sulfur dioxide emissions and nitrogen oxide emissions. And what we see is that overall there are strong decreases in sulfur dioxide emissions across all the countries, and especially strong decreases in countries where power generation used to be running on coal, and the alternative was a fast increase in solar photovoltaics and wind. So it's rather a positive figure that emerges. There are some countries where there is a slight increase, very, very small. And in these cases, when it's possible to drill down with this tool that we provide, when you drill down, you realize that the increase is coming against the backdrop of an increase in solid biomass use and biogas use as well, and somewhat lower consumption of natural gas in the against the counterfactual. So then in that case, there is a slight increase in the emissions. Moving also further to the next slide, when we look at particulate matter and volatile organic compounds, there the picture is more mixed than for sulfur dioxide, where in general there are very large reductions. So for particulate matter and volatile organic compounds, what we see is that the combustionable renewables can have some effect, and they have increased. So there can be some interactions with solid biofuels leading to higher emissions of dust, of particulate matter, and also to volatile organic compounds. And increases appear mostly in the countries where these technologies have increased most, whereas in countries where biomass-based electricity combustion has gone down a little bit compared to 2005, you're going to see decreases. Also with the same tool, it's possible to drill further down at the country level. And here is one simple example for Germany, showing on the one hand the interaction with sulfur dioxide emissions. Germany is a country using a lot of coal, so there is no surprise here that the reduction in sulfur dioxide emissions is very large. It's mainly because of, or thanks to solar photovoltaics coming in, but also onshore wind and offshore wind. When we look at particulate matter, we also see a significant decrease for Germany and a very small increase, which is what I was referring to before, when combustible biomass, solid biomass in most cases, increases compared to 2005 and gives rise to these interactions. My second to last slide, actually, among the co-benefits that we show, we also look at the interactions with the primary energy target that the European Union has set for 2020. And what we see and what we know is that depending on the interplay between renewable electricity technologies and the other technologies in the mix, there may be some statistical efficiency improvements. The transformation efficiency, for example, for wind power is 100%, for photovoltaics as well, which means that there is a slight reduction in the primary energy equivalent from moving towards renewable electricity. In this case, when we calculate it at the European Union across all the market sectors, so renewable electricity, heating and cooling and transport, we see a roughly 4% reduction in the total primary energy consumption, which is also interesting. And my last slide with the conclusions is that we do see an essential role for renewable electricity in climate mitigation. It is absolutely clear. And it is also important not to lose momentum in this sense and to keep in mind the fact that we are looking ahead at the Fit for 55 package with more ambitious targets for 2030 and 2050. It's also true that an increasing share of oxidizable, so non-combustible technologies in general decrease the negative interactions with air pollutant emissions. Whereas on the side of combustible technologies, the interaction can be mixed and they depend a lot on the type of plant where the biomass is being combusted, the type of process emissions. So there are many factors there, and also the uncertainty in our estimates is slightly larger. Of course, everything will be much more relevant at European level, and at the specific technology level, there are other conditions that prevail. So these are in the end to be treated as indicative estimates. A further point is that reducing energy consumption is key, as I was showing before, because it will help substitute more rapidly more non-renewable sources. From the greenhouse gas perspective, obviously, it's really important to substitute the most carbon-intensive fuels first, so coal first. But there might be other national profiles and objectives that need to be taken into account. And finally, with the tools that we're providing, we hope that we're helping policymakers to understand these interactions at the sectoral level and how the national paths that are being chosen can lead to some particular trade-offs and take into account these trade-offs and design the most optimal strategies at the national level. I leave you with this, and I will hand over, I will continue sharing the slides on behalf of my colleague, Evert Baumann, who will continue this presentation from the perspective of a life cycle analysis. So going broader than the sectoral interactions and going into life cycle analysis. Evert, the floor is yours.
Thank you, Mihai. Thank you, Hans, also for this invitation. I'm very happy to present to you some of the work we have been doing for the European Topic Center on Climate Change, Mitigation and Energy. And so today I will be taking you through some key results of an AONet working paper that we provided about a year ago. We wrote it in collaboration with Mihai at the European Environment Agency. My name is Evert Baumann. I work as a senior scientist in the Department for Environmental Impacts and Sustainability at the Norwegian Institute for Air Research. But today I'm speaking in the capacity of, as an institute, we are part of one of these European topic centers, the European Topic Center of Climate Change Mitigation. Mihai, could you please change the slide? Perhaps some background on what these European topic centers are. They are centers of thematic expertise that are under contract, under framework contracts by the European Environment Agency, and meant to support the European Environment Agency with the implementation of their work program. There are 8 European topic centers. They cover quite a wide variety of areas. And today I'll be presenting from climate change mitigation, but there is a European topic center on health and environment. There's a European topic center on circular economy, on digitalization. So there's various subject areas covered. We are a consortium. At the moment, the ETCCM, the current ETCCM that started in January 2022, is 15 different organizations based out of 10 different countries, and it's led by VITO, the Flemish Institute for Technological Research. Next slide, please. So while Mihai has been talking primarily about the overarching energy system and renewable energy sources within the energy system in his previous presentation, here we intend to drill down in the electricity sector, specifically the gross electricity production in the EU 27. And we know that electricity production in itself is a significant contributor to greenhouse gas emissions in the EU. At the same time, during operation, specifically for the non-combustion renewable electricity sources, such as wind power or concentrated solar power or photovoltaics, here the emissions are virtually zero. But at the same time, we see that the construction of all this infrastructure is both material and energy intensive, which then therefore may lead to emissions further upstream the value chain. And where there are emissions from a life cycle perspective, there are potential environmental impacts. And this is illustrated by a report from the International Resource Panel under UN Environment Umbrella in 2016, using data from 2010, where essentially there are already shown trade-offs between different renewable energy technologies vis-a-vis the fossil fuel technologies. Next slide, please, Mihai. And so for the ETCCME, so this was the previous European Topic Center, Climate Change, Mitigation and Energy. We studied the life cycle impacts of electricity in a specific period. So looking retrospectively from 2005 to 2018, using or basing our model of life cycle assessment. And for those that don't know life cycle assessment, it's really a tool to quantify potential environmental impacts of either products or services or processes throughout the life cycle. So taking a value chain perspective, if you will. And what's special about life cycle assessment is that it's both quantifies and attributes the direct and indirect requirements associated with demand for a product. And by that, I mean that you're not only looking at the emissions at the power plant level, but also at the indirect emissions associated with, for example, the fugitive emissions for the extraction of natural gas. Now, one of the key modeling components of life cycle assessment is called a life cycle inventory. And each inventory is literally a description of processes along the value chain, documenting both inputs and outputs to and from the economy, and documenting the emissions and the resource extractions from environment. And based on that, you can then, combining with life cycle impact assessment, come to what we call life cycle impacts, and these impacts are then expressed in impact indicator potentials, such as the global warming potential, or freshwater ecotoxicity potential, or particulate matter formation potential. There are many, many more, but for this presentation, I will focus on these three. Next slide, please. And as Mihai, I will present an overall approach. So we take a life cycle based approach. We start out with a collection of life cycle inventories for different electricity production technologies. For example, hard coal combustion in a power plant, or a natural gas combined cycle power plant. We then take these life cycle inventories and adapt them using energy balance statistics. And this is very much the same energy balance statistics used for the previous presentation. So this is Eurostat data directly from the energy balances or from the shares questionnaire. And we then make sure that we have a life cycle inventory per member state and per year of the EU 27 in this period 2005-2018. Subsequently, we calculate life cycle impact intensities, and a life cycle impact intensity is, for example, a carbon footprint, a kilogram CO2 equivalent per kilowatt hour of energy produced, of electricity produced. And we have these for different impact categories, for different impact indicators, and per source, per energy source, per member state, and per year. Subsequently, we scale up with annual electricity production, and similar to the previous exercise, we define a counterfactual scenario whereby comparing the counterfactual scenario with the historic scenario, we calculate what we call the gross avoided potential environmental impacts. And just to give an overview of how one of these life cycle inventories is built up on a very overarching and abstract level, there is what we call a life cycle inventory database. And then for the combustion technologies, we have at minimum fuel extraction and fuel transport processes. And then for the rest, we have also power plant infrastructure, power plant operation, and power plant decommissioning. And so we do what is called a cradle to gate life cycle study, where we shut off at the delivery of electricity to the grid. Next slide, please. And here is really one of the key slides in terms of the trends for electricity production in the EU 27. To an extent, Mihai has already presented this, but we see on the left-hand side the shares of the different energy sources that are incorporated in our model for both 2005 and 2018. And on the right-hand side, we see the absolute gross electricity production in terawatt hours in the EU 27 for those same energy sources. And starting with the right-hand side, you can basically see that the overarching the renewables, they increase much more. You see much more onshore wind, offshore wind coming in. You see biomass, solid biomass growing, as well as photovoltaics really kicking off. That is different per member state. So on the left-hand side, on the 2005 figure, you can, for example, see Denmark and Germany. They don't have too much renewable energy in their system, but in 2018, this has differed quite substantially. So specifically in Denmark, there's quite a lot of blue bars there, and Germany also the blue bars have increased. Next slide, please, Mihai. And so when we then do our calculations, we come up with very similar graphs as to in the previous study, but this time we look at the life cycle perspective emissions. And so we're only looking at the electricity system, I should stress that. But for these three impact categories, impact indicators that I have described before, we see on the bottom line our historic scenario, the greenhouse gas emissions go down, for example, and in our counterfactual that has the renewables set at the 2005 level, frozen at the 2005 level, we see much higher emissions. And by taking the cumulative avoided emissions, we come to a figure of about 1,800 megaton of CO2 equivalent avoided. We see a similar story for particulate matter formation, which is not surprising since when you combust coal or another fossil fuel, you will have both carbon dioxide as well as particulate matter type emissions, and we see also here a relatively high amount of PM10 equivalent emissions avoided. What's interesting though is that on the ecotoxicity side, we see the other behavior. So we see that the actual values are higher than the values when there would not have been so much renewables in the mix. And this is partially because some of the renewable energy technologies are relatively infrastructure intensive, which means that upstream in the value chain, there is more mining going on, for example, and there may be emissions of metals into the environment, leading to higher freshwater ecotoxic potential impacts. The unit here, 1,4-DCP, is 1,4-dichlorobenzene equivalent. Next slide, please, Mihai. Now, if I now go break this down, these same different impact categories to the contribution of each of the renewable energy sources to avoided impacts. Here, it's important to note that positive is avoided and negative is actually net added. On the greenhouse gas emissions, we see that all the renewable energy sources actually contribute to gross avoided impacts, whereas on the particulate matter, we see that some renewable energy technologies, and this is basically solid biomass, they will have a negative effect on avoided emissions, but this is balanced out by the positive effects of all the other renewable energy sources. Again, I mentioned that in freshwater ecotoxicity, we actually had a net addition, and this is mainly due to upstream and emissions associated with the PV value chain, as well as emissions associated with the combustion of the renewable fraction of municipal solid waste. Next slide, please. And so concluding, if we really look at the drivers, we see that our energy transition to renewable energy sources is really a change from a throughput intensive to an infrastructure intensive combustion technology. So we combust coal or we combust natural gas, but we are now building a wind turbine, and that means we need to have the materials to have this wind turbine. Biomass combustion here is of course an exception because that's still combustion-based technology. Life cycle impact indicators are therefore also more associated with the infrastructure value chain compared to what previously was the fuel value chain. We need more materials to produce similar amounts of electricity, and this actually has consequences for global material supply chains. And if you look at especially the makeup of newer technology, there's a lot of critical raw materials in these technologies, right? So wind turbines, photovoltaics, they rely on specialty metals, and this means that we have also potentially a resilience issue. And so here we see that the trade-offs really of the renewable energy transition are that we have a criticality issue potentially, and we need to think about what to do with the material supply. Nevertheless, our climate and air pollution benefits are significant. So there are, I don't want to say that there are no benefits to renewable energy, it's quite the opposite. But when we look at the life cycle perspective, we can actually aid in designing strategies to even lower the potential trade-offs associated with the renewable energy transition, for example, through implementing better material recovery at the end of life of renewable infrastructure. And this means that you both reduce the impacts associated with primary material production, so you reduce upstream impacts at the same time as you reduce your dependency on critical resources, and you're contributing towards a circular economy. Next slide, please. Similarly, there are power plant lifetime extensions that may help to mitigate trade-offs from increased use of infrastructure in renewable energy sources. The longer you use a wind turbine, crudely put, the lower its impacts per unit energy or per unit electricity generated will be. The same holds for the energy and resource efficiency. So throughout the value chain, you can have increases in these also in the biomass combustion technologies, and this will lower than impact intensities. And I've mentioned already that circular strategies may reduce impact intensities as primary resources are avoided. There are, of course, in such a study, there are some uncertain aspects. So we had to do a compilation of different data sources of varying quality. So there are some uncertainties associated with this. The results may be sensitive or are sensitive to say single environmental emissions in individual life cycle inventories. And of course, today I only presented 3 different impact categories. And so that means that there are other relevant impact categories that I haven't talked about, also that are not so well reflected in life cycle assessment framework. Examples are noise or biodiversity impacts. And then I have a final slide, Mihai. Next slide, please. Yes, simultaneously we see that there is an absolute decrease in the potential impacts in the period 2005 to 2018. This is, we see that the gross avoided impacts for the electricity system, they are really driven by, if I would prioritize onshore wind, solar PV, and bioenergy sources. In today's presentation, there is a cost in terms of freshwater ecotoxic impact. I believe that cost is definitely worth it compared to the main benefits associated with climate change as well as air pollution. And these costs are also compensated by using different or combinations of different renewable energy sources to produce electricity. More importantly, while transitioning, we should not forget other type of mitigation efforts. For example, increase in efficiency, implement emissions mitigation technology, and also, lifetime extension I have mentioned, and increased use of secondary raw materials. So recovery of materials, reuse of different parts of renewable energy infrastructure. And with that, I would like to conclude and thank you for your attention.
So thank you, Evert and Mihai. So let me then pass the floor now to Yamilia to take us through the panel. So Yamilia, the floor is yours.
Thank you very much. And let me start with, as a board member of the Energy Evaluation Europe International Conference, I would like to thank you both for your lovely presentations. I think they give very nice insights in the matter, and we'll come back to that in a minute. And of course, I would like to thank Copper8 for this joint webinar. Having said that, let's start with a general question. Well, you both make use of certain types of methods, etc. And as we have a very diverse public and audience today, people that are familiar with the LCA and people that are familiar with energy evaluation methods, I can imagine that it's good to hear as an audience where the drawbacks of your studies lie. So what should the audience know when looking and hearing your presentations? What do you think is important for them to know? Could you elaborate, Mihai, to start with?
Yes.
And after that, Evert.
Very good. Thanks. Thanks so much. Yes, it's a very good question. We tend to say all the time, look into the direction of travel and consider these estimates. I think there are many sensitivities or many aspects that relate to the sensitivity, but probably the most important area relates to the interaction with air pollutant emissions. This is, as I was indicating before, because there are so many drivers or so many factors that play an important role. The type of fuel, the type of technology, the type of abatement on the type of technology, the type of operating the technology, so the operating hours having an impact ultimately on the efficiency parameters. So there, the interactions are, of course, more difficult and more indicative of a direction. Nevertheless, we think that the direction and that the estimates are actually relevant, and we have tested the tool and we have tested the methods against the energy balances. And it's quite interesting when you start digging into what's happening actually there. Whoa, I see something in a particular country on one interaction. Why so? And it's very interesting to dig down there and to see the corresponding data and information from the energy balances, for example, or from the renewable energy shares, which explains what has happened. But that would be the area where I would say the largest sensitivity is around the tool that I have presented. The other point I would like to mention is also that we treat biomass in a from a sectoral perspective. That means we do not really assume it is carbon neutral by default, but we also do not take into the model the interaction with the land use change and forestry part. And as we know, this is really ideally one single system and treated as one single system, because what's being taken up on the one side, for example, by growing forests, is actually emitted on the other side. But we do not take the emissions and we do not take the interaction with the land use change and forestry part into these assumptions. We just say, we assume it's being taken up. But perhaps a future development could be to try to go further around that, but it will take some time until we have a good understanding for this dimension.
Okay, and just to make sure that energy efficiency wasn't part of your evaluation?
Yes, it's energy efficiency. It's more represented here, and I would try to take this opportunity to respond also to the first question. It is more of a bycatch of what is happening when we look at these methods and what we know is being used as the primary energy equivalent methods from Eurostat. So I think here, when you look at wind energy, the conversion or the primary energy of 1 unit of final energy consumed from wind or generated by wind is 1 unit primary energy as well. So it's assuming a 100% transformation. Of course, if you look at another fuel, if you take, for example, a fuel with a 50% efficiency, what happens is that you suddenly need 2 units of primary energy to produce that 1 unit of final energy, which is being substituted in the method, which leads to an efficiency improvement in primary energy. If you want to put it like this, it could be put on the back of the statistical improvements, but also, sorry, of the statistical methods, but also the fact that these technologies like wind and solar PV have a direct conversion. But it is not an actual efficiency or energy saving across the fuel.
Okay.
If you want to put it, yeah.
Yeah, okay, very clear. And Evert, what would you say are drawbacks of the LCA the audience should be aware of?
Thanks, Yamilia, for also this question. I would say that the drawbacks of LCA are those that are generally applicable to any type of footprinting method, right? So life cycle assessment really is a tool that was meant to identify hotspots in a value chain that can compare different product systems to each other, and out of necessity, then needs to reflect quite some complicated processes within the value chain. And whenever I do life cycle assessment, or as a practitioner, I see, say, 2 different approaches. One is the approach we have presented here today, which is really a top-down approach. And by that, I mean we take a relatively generic model of a combustion technology or of a renewable energy technology, and manipulate this based on the external statistics from Eurostat. That means that if you go look at a specific site, at a specific wind turbine park offshore of the Netherlands, for example, then you will get different results, either because you have much better data within your model, because your transport distances are suddenly of all the materials, they are defined, and this is something we don't have in our modeling. And so that means that these type of top level models, they have a fair amount of detail in them, but they are still not state of the art when you're looking, or when you're trying to explain individual technologies or individual locations with them. Simultaneously, compared to some of the other models out there, they are much more detailed, perhaps, than models that only look at a fairly small amount of emissions. And so I find myself often in the middle of 2 different perspectives, either the very macro perspective, where what we do is already too detailed, and on the other side, the perspective of people that work on a much smaller regional scale, really on individual products, individual locations, and then what we do is too crude. And what's important, I think, here to take away is that we're really talking about the big trends, and the big trends are not going to change, not going to be influenced by these types of uncertainties, right? If we're putting it crudely, the combustion of a kilogram of coal will always result into a fairly high amount of carbon dioxide compared to the electricity production from a wind turbine. And so those are order of magnitude differences. And this is where life cycle assessment is a pretty good tool to look at the carbon footprints.
Okay, thank you for your answers. Now we've spoken mainly about environmental impacts and effects and indicators. As an energy evaluation community, we realize more and more that the transition towards less carbon dioxide and so a cleaner energy system means also that we need to take into account other impacts than only the carbon dioxide reduction. Now, you've shown a few effects here, which we should take into account. Are there other effects you think that should also be taken into account, not discussed today? And Evert, I'll give the floor first to you.
Well, typically we distinguish between what we call midpoint and endpoint impact categories. And I see in the chat already here mentioned, what about radioactive waste or about nuclear waste? And this is something that could be included as an impact indicator. There is ways of quantifying actually health impacts expressed in what we call disability adjusted life years. We have chosen not to present this here in this particular report, but it's possible. Biodiversity I already mentioned in the presentation. I think it's quite interesting to look at the interplay from climate mitigation strategies and what this means on, say, the production side, and also what this implies for biodiversity. There are some biodiversity indicators within the life cycle assessment method, but they are still relatively crude. And well, simultaneously, one could even bring this, but then we're out of our field or my field of life cycle assessment into socioeconomic indicators that could also reflect upon the just transitions, for example. But yeah, I'll leave it there.
Okay, thank you. Mihai?
Not really much to add. I think looking backwards, we're quite happy that we moved from discussing the sectoral interactions to broadening and to trying to understand the bigger picture, which is what Evert presented, because of course it matters. It also indicates where we can improve certain things. I would concur that biodiversity is one area where we understand it's a little bit harder to understand the interactions and the impacts. Because it is very specific, it's very location specific, and it reacts very differently to any particular types of impacts. The other parts that could be interesting would be the socioeconomics, so trying to bring in socioeconomic dimensions and trying to understand how we address these or particular vulnerabilities there.
Okay, thank you. And then my last question for now, and then I'll give the floor back to Hans, is what are your future research steps you will take in relation to the presentations you've given us today?
All right, I can, yes. If I am to start on that, we are trying to understand how we can expand the current assessment that we have done for the electricity part, the life cycle assessment, to try to model it for the heating part so that we have a complementary approach and understand better the interactions that happen when we move to more and more renewable heating.
Thank you. Looking forward to that. And Evert?
Well, I'll second that because I'm working with Mihai on particularly this topic now in the ETCCM. Perhaps in addition, I would like to add as an interesting research topic that we are engaging with is really the interplay between climate change mitigation and circular economy, particularly when we're talking about near future waste streams coming from renewable infrastructure. So it's the wind turbines that are currently being dismantled, or say within the next 5 to 10 years will be dismantled. How can we ensure that those resources are not lost? Are there opportunities there? And what are the environmental implications of this? So both heating as well as working with the effects of waste from renewable energy infrastructure is high on our agenda.
Okay, thank you. Looking forward to hearing more about this. Hans, I'll give back the floor to you.